Hello and welcome. In this video, we will program a snake game in C# using WPF for the UI. My game will look exactly like this, but you can easily change the size of the grid or how fast the snake moves. Ouch. Let's open up Visual Studio and get started. First, we must create a new project for the game. The project template we need is WPF application. I will call the project Snake. And for the target framework, I will use .NET 6.0. Before we begin, open the Solution Explorer. Right-click on your project, go to Properties, and then go to Build, General. Depending on the version of .NET you are using, Nullable may be enabled by default. This feature is supposed to help you avoid null reference exceptions, but I think it can be confusing, so I will disable it. If you enable it, then everything will still work, but you might see some warnings. Alright, let's import the assets for this game. To keep things organized, we start by creating an assets folder. Here are the assets for the game. You can download them from the link in the description of this video. There's an image of the snake's body and its head. We also have darker versions, which are for when the snake dies and the game is over. Then there is the food, of course, and an empty square as well. Note that all of these images have a border, so they form a grid when they are placed next to each other. Finally, we have the font we will use, and this S, which will be the application icon. To import them, just drag and drop them into the assets folder. Inside Visual Studio, select all of them. Right-click, go to Properties, and set Build Action to Resource. This will embed the assets inside the game's executable. Great. We have now set up the project. Before we start coding, let me explain how we will represent the game. Snake is played on a grid like this one. Of course, during the game, this grid won't be empty. Some positions will be occupied by the snake, and one position will contain food. My grid has 15 rows and 15 columns, but you can choose a different size if you want to. We use the convention that rows increase from top to bottom, so the origin at row 0 and column 0 is the top left position. The grid will be represented using a two-dimensional array. Empty positions are represented with value 0. Positions containing part of the snake are represented with value 1. Note that this includes the snake's head. There is no special value for that. The position containing food is represented with value 2. Our code will be easier to understand if we have names for these values. So let's begin by creating an enum for them. Back in Visual Studio, I will add a new class called GridValue. We don't need any of the imports at the top. And I will change it to a public enum. a position in the grid can be empty. It can contain part of the snake, or it can contain food. I will also add one more enum value here called outside. This value won't be stored in the grid array, but it will be convenient in the code when the snake tries to move outside the grid. The next class we need represents a direction in the grid. We encode a direction as two integers, a row offset and a column offset. This will make sense in a minute. First, we add a private constructor, which takes the row and column offsets as parameters. In the body, we set our properties equal to these values. Because the constructor is private, no other class can create an instance of the direction class. And that is intentional. We only need 4 directions, left, right, up and down, which we will add as static variables. To move left from a given position in the grid, we must leave the row unchanged and subtract one column. Therefore, the row offset should be 0 and the column offset should be -1. To move right, don't change the row, but add one column. To move up, subtract one row and don't change the column. And finally, to move down, add one row and don't change the column. Let's add a method called opposite. It will be convenient later. As the name suggests, it returns a direction's opposite. The easiest way to do this is to return a new direction with opposite row and column offsets. Next, I want to override equals and get hashcode, so the direction class can be used as the key in a dictionary. This can of course be done manually, but it's easier to let Visual Studio do it for us. Just press Ctrl dot and then choose generate equals and get hashcode. Both row offset and column offset should be used, so make sure they are checked. And if we check generate operators, then it will also overload the equality and inequality operators. Voila! Now we have meaningful implementations of equals and get hashcode. We also have overloads of the equality and inequality operators, so we can use them to compare directions. Perfect. We also need a class that represents a position in the grid. this class stores a row and a column. Let's add a constructor which takes the row and column as parameters. In the body, we save these values in our properties. Next, we need a method called translate. It returns the position we get by moving one step in the given direction. So we return a new position here. The row should be this position's row plus the direction's row offset. And for the column, we need this position's column plus the direction's column offset. Just like for the direction class, we want to override equals and get hash code. And of course, we want the operators as well. As you can see, it generated something very similar to what it did in the direction class. Alright, now we have all the little helper classes we need to implement the game logic. Let's create a class which stores the current state of the game. I will call this class GameState. We need a few properties here. The number of rows and columns in the grid, and then the grid itself, which is a two-dimensional rectangular array of grid values. The snake also has a direction, which dictates where it will move next. And then we need a score property. And finally, a game over boolean. It will also be convenient to keep a list containing the positions currently occupied by the snake. We use a linked list because it allows us to add and delete from both ends of the list. We use the convention that the first element is the head of the snake and the last element is the tail. The final variable we need is a random object. It will be used to figure out where the food should spawn. Next, we need a constructor. It takes the number of rows and columns in the grid as parameters. First, we store these numbers in our properties. And initialize our 2D array with the correct size. At this point, every position in the array will contain GridValue.empty because it's the first enum value. When the game starts, I want the snake's direction to be right. Let's create a method which adds the snake to the grid. I want it to appear in the middle row in column 1, 2, 3, as you can see here. First, we create a variable for the middle row. If you use an even number of rows for your game, then this row will be slightly closer to the top. Next, we loop over the columns from 1 to 3. Inside the loop, we set the grid entry at r, c to GridValue.snake. We must also remember to add this position to the snake positions list. Now we can call addSnake from the constructor. We also need to add some food. Let's start by creating a method which returns all empty grid positions. Here, we loop through all rows and columns. Inside the loop, we check if the grid at r, c is empty. If so, we yield return that position. Now we can write the addFood method. First, we create a list of empty positions. It is theoretically possible to beat snake, in which case there wouldn't be any empty positions. If someone actually does that, it would be a bummer if the game crashed. So, if there are no empty positions, we simply return. In the general case, we pick an empty position at random. And set the corresponding array entry to GridValue.food. Another way to do this would be to repeatedly generate random positions and check if they are empty. If you choose this approach, then just make sure you have a way of detecting when there are none of them. Okay. addFood should be called in the constructor, just like addSnake. Great. Let's add a few snake-related helper methods. The first one returns the position of the snake's head. We can easily get this position from the linked list. We need a similar method for the tail position. we can get this position from the other end of the list. The next method returns all the snake positions as an IEnumerable. Note that these methods are public. Later, we will use head position to add eyes to the snake, and you could also add a special tail using tail position. The snake positions method will be handy when the snake dies and we turn it dark green. Next, we will add two methods for modifying the snake. The first one is called addHead. It adds the given position to the front of the snake, making it the new head. So we must add this position to the front of our list. And set the corresponding entry of the grid array to GridValue.snake. The next method is for removing the tail. We start by getting the current tail position. Then we make that position empty in the grid. And remove it from the linked list. These two methods will be super useful when we have to move the snake. Great. Now we need to add some public methods for modifying the game state. The first one changes the snake's direction. For now, it will simply set the direction property to the direction parameter. This is a bit too simplistic, but we will come back and change it once the problem becomes apparent. We need a way to move the snake, so let me show you how that works. Here is an example game state. The snake's direction is up, so it should move to this square here. To do this, we actually don't have to move all the snake positions. We just have to remove the tail and add the new head position. Remember that there is no special grid value for the head. So if we look at the 2D array, then the move looks like this. We set the tail position to 0 and the new head position to 1. That is the general case, but let's take a look at this state here. The snake's direction is left, but there is food at that position. In this case, we do not remove the tail. We simply add the new head position. So now the snake is a little bit longer. Here is another state. This time the snake's direction is right, but it cannot move that way because it would move outside the grid. In this case, we won't move anything, but the game will be over. The same thing is true for this state. The direction of the snake is down, but moving down would make the snake hit itself. So nothing has to be moved, and the game will end. Let's open up the editor again and implement these cases. First, we need a method which checks if a given position is outside the grid or not. The next method takes a position as parameter and returns what the snake would hit if it moved there. I call this method will hit. In the general case, it will just return what is stored in the grid at that position. But there are two special cases we must handle. If the new head position would be outside the grid, then we return our special grid value called outside. Let me show you the other special case. In this state, the snake's direction is up, so the new head position would be where the tail is currently at. What should happen in this case? In my opinion, the tail and head move simultaneously, so the move should succeed like this. To handle this, we must check if the new head position is the same as the current tail position. And if it is, then the tail will move out of the way and that square will be empty. Maybe it makes more sense to you that the game should end in this case. If so, then just get rid of this check. Alright, now we can write a public move method. It will move the snake one step in the current direction. First, we get the new head position. Then we check what the head will hit using our will hit method. If hit is GridValue.outside, or GridValue.snake, then we set game over to true. If the snake will move into an empty position, we remove the current tail and add the new head. And if it hits a position with food, then we don't remove the tail, but we do add the new head. We should also increment the score and spawn the food somewhere else. We will return to the game state later to fix a few things, but for now, let's load the image assets. I will just close the three classes that we are done with and add a new one. This class will be called images. Let's make it a public static class. This class will basically be a container for all our image assets. We can get rid of all the imports except for system. We also need system.windows.media, and system.windows.media.imaging. For convenience, let's add a private method called loadImage. It loads the image with the given file name and returns it as an image source. Now we can add static variables for each of our image assets like this. And similarly for the rest of the images. If you are coding along with me, just pause the video and add all of them. Next, let's open up app.saml. Here we will define a few color resources and prepare the font for our game. We start with the background color. I'm using a dark purple color. We also need a background color for the grid. This color is a slightly brighter shade of purple. I will also add the color of the grid lines. This is the same color I have used for the image assets border. Next up is the text color. It is almost white, but not completely. The final color we need is for an overlay, which will be displayed on top of the grid before the game starts. This color is black with around 50% opacity. Remember that we also have a font in the assets folder. We will also add that as a resource. Now we have everything we need to code the UI. So let's open up main-window.saml. Here I will set the window title to snake and the initial height to 500. Next, we set background to our background color resource. And foreground to text color. And font family to our main font. The controls we add to the window will inherit these values by default. Let's make the window open at the center of the screen. And set the application icon. For the layout, we need 2 rows. The top row has height set to auto, and the bottom row will use the remaining height. In the top row, we will display the score. For that, we can use a text block. We will call it score text. And center align it horizontally. And vertically as well. Initially, the actual text should be score 0. It's currently too small, so let's set the font size to 22. We will also set the margin to 10. The bottom row will contain the grid where the game is actually played. Let me show you how that will work. As we have seen, the game state contains a grid array like this one. In the UI, we will add a grid of image controls with the same number of rows and columns. The idea is that this grid of images will always reflect what is stored in the game state. For an empty grid position, we show the empty image asset. For a snake position, we show the body asset. And for the food position, we show the food asset. Later, we will also add eyes to the snake using the head asset. And when the snake dies, we will use the dead snake images as well. We are not going to draw grid lines explicitly. All we have to do is place the image assets next to each other and give this grid of images a background color. One drawback of this approach is that the edge lines are only half as thick as the inner grid lines. To fix that, we will add an outer border with the grid line color. Okay, so first we add the outer border. Let's name it grid border. And place it in row 1 of the main grid. The border should have the same color as the grid lines. And I will set the thickness to 1.5. Inside the border, we will add a uniform grid for the images. Its name should be Game Grid. It's important that each cell in the grid is a square. If the cells are rectangular, then our game won't look right. So let's set the width and height to 400. The size of the grid must match the number of rows and columns you use. So if you have twice as many columns as rows, then the width must be twice the height. For the background, we use our grid background color. There is a small problem here. I think you can see what it is if I change the thickness of the border to 10. The middle square is our uniform grid, but the border doesn't fit tightly around it. That's because the border's horizontal and vertical alignment are set to stretch by default. So let's set both to center. Beautiful. Now we can set the border thickness back to 1.5. Before anything interesting can happen, we must add image controls to the game grid. But we will not do it here. Instead, we will add the images from main-window.saml.cs, which is known as the code behind. Here we need two variables for the number of rows and columns. I'm using 15 rows and 15 columns. Next, I will add a 2D image array for our image controls. This array will make it super easy to access the image for a given position in the grid. Now we can write a method called setUpGrid. It will add the required image controls to the game grid and return them in a 2D array for easy access. We start by creating a 2D array. Next, we have to set the number of rows and columns on the game grid. Then we loop over all grid positions. For each of them, we create a new image. Initially, I want its source to be the empty image asset. We store this image in the 2D array. And add it as a child of the game grid. Outside the loops, we return the images array. In the constructor, we call this method and save the returned array in grid images. Let's try to start the program. We have a grid. Nice. But if you squint, you may notice that there are small gaps between the images. Our current setup also doesn't do a good job at scaling them. To fix both issues, go to main-window.saml and locate the uniform grid. Here we will set snaps to device pixels to true and render options.bitmap scaling mode to high quality. That's better, but you might still see a small gap between the border and the grid. To fix that, go to the border and set render options.edge mode to aliased. Great. Now everything looks how it should. Let's make this game playable. We need event handlers for 2 window events. The loaded event and the key down event. Back in the code behind, we will add a dictionary which maps grid values to image sources. If a grid position is empty, we want to display the empty image asset. If a position contains part of the snake, we want to show the body image. And if a position contains food, then we show the food image. Note that I have omitted the type after the new keyword. You can only do this in newer versions of C#, so if you are having problems, then just write the type again. Okay, we also need a game state object. Which we initialize in the constructor. Now we can write a method called drawGrid. This method will look at the grid array in the game state and update the grid images to reflect it. It loops through every grid position inside the loop. We get the grid value at the current position and set the source for the corresponding image using our dictionary. We will call drawGrid from a more general draw method. Right now it's a bit redundant, but it will do a few more things soon. Alright, let's scroll up to window loaded. Here we will call draw. And then start the program. We have a visual representation of the grid. Now we just have to handle some keyboard inputs. This window key down method is called when the user presses a key. If the game is over, then pressing a key shouldn't do anything, so we simply return. Otherwise, we check which key was pressed. I will use the arrow keys, but you can use other keys if you want to. If the user presses the left arrow key, we change the snake's direction to left. And similarly for the other arrow keys. Now we can change the snake's direction, but we need to move it at regular intervals. For that, we add an async game loop method. The loop will run until the game is over. In the body, we add a small delay. I'm using 100 milliseconds, but you can change this to make the game slower or faster. After the delay, we call the move method. And then draw the new game state. That's it for the game loop. Now we can make window loaded async. And start the game loop. Check out the program now. The snake moves and we can change its direction. When we eat food, the snake grows. And if I die, then the snake simply stops moving. Note that the score did not change when the snake was eating, but that's easy to fix. In draw, we set the score text to score. Followed by the actual score stored in the game state. Now the score updates when the snake eats. But there is another problem. Watch this. The snake stopped moving, which means the game is over. But why? Well, it's because the snake was moving down and then I pressed the up key. Let me explain. Here is an example game state. The snake's direction is up, but then the user presses the down key. In our current implementation, this will immediately change the direction to down. This is bad, because now the snake tries to move here. That position already contains part of the snake, so the game ends. Obviously that shouldn't happen, but how do we fix it? Here is an idea. We should never change to the opposite direction. So in this example, where the direction is up, pressing the down key should do absolutely nothing. This is a great idea, but it's not quite enough. Consider what happens if I quickly press right and then down before the snake has a chance to move. The direction will change to right, and immediately after that, it will change to down. When it's time to move, we have the same exact problem as before. But what should happen in this case? Ideally, it should move right first and then move down next time. Here is how we can accomplish that. When the user presses a key, we don't change direction immediately. Instead, we save direction changes in a buffer. You can think of them as predetermined moves. When it's time for the snake to move, we check the buffer, If it's not empty, we get the oldest entry, set the snake's direction to that, and then move it. For the next move, we do exactly the same. We must still avoid changing from one direction to its opposite and filling the buffer with redundant direction changes. How that works will be clear when we implement this in code. So let's do that now. First, we navigate to the GameState class. Here we add a variable for the buffer. A linked list is a good choice for the operations we need. In change direction, we won't change the direction immediately. Instead, we will check if the change can be made. And if so, add it to the buffer. In a minute, we will replace the comment by an actual check. To implement it, we need a helper method called getLastDirection. It returns the snake's last predetermined direction. So if the buffer is empty, it just returns the current direction. Otherwise, it returns the last or most recently added direction change. Now we can implement canChangeDirection. It returns true if the given direction can be added to the buffer, and false otherwise. If there are already two direction changes stored in the buffer, then we consider the buffer to be full and return false. You could also use 3 as the buffer size, but it is important to have a maximum size. If not, the user could spam keys and predetermine the snake's movements way too far into the future. If there is space in the buffer, we get the last predetermined direction and return true if the new direction is not the same as the last direction, and they are not opposites. Great. Let's replace the comment in change direction. With the actual method call. Now we just have to make a small change in the move method. We check if there is a direction change in the buffer. If so, we change the snake's direction accordingly. And remove that direction change from the buffer. That's it. Let's see if it works. Now I cannot lose the game by making the snake move in the opposite direction. And if I click 2 keys very quickly, then the snake performs both direction changes in sequence as intended. It starts to look like a real game now, but look what happens when I resize the window. The game doesn't scale very well at the moment. Let's go to main window.saml. We are going to wrap the main grid in a view box. So I'll select the entire grid, cut it, then add a view box and paste the grid inside. If you look in the designer to the left, you can see that there is no space underneath the actual game grid. So on the border, we're just going to add a small margin. And it's probably a good idea to set a minimum width and height for the window. Now the game scales much better. At the moment, you must be ready to play as soon as the program starts. We are also lacking a way of restarting the game, so let's work on that now. In main window.saml, we add a dark overlay with some text on top of the game grid. This overlay will be inside the main grid. Here we add a border called overlay. It must be in row 1. And have the semi-transparent overlay color. This border must have the same size as the grid border. We could do this manually, but there is a more convenient way. We bind the width to the actual width of the grid border. And same thing for the height. We must also use the same margin. And we also set edge mode to aliased. This should ensure that the overlay takes up the exact same space as the grid border. Inside the overlay border, we add a text block. Let's call it overlay text. And set the text to press any key to start. It looks a little small, so let's set the font size to 26. We will also center align it, both horizontally and vertically. I will also set text wrapping to wrap. This will make sure that the text fits inside the overlay, even if you have more rows than columns. Perfect. Let me scroll to the top. Here we have this event handler for the loaded event. We don't actually need it anymore, so you can just get rid of it. What we do need is an event handler for the preview key down event. I will explain how it works in a second. Let's navigate to the code behind. We start by adding a boolean called gameRunning. It is false by default, which is what we need. Next, we turn window loaded into a regular async method called runGame. This method should also hide the overlay. When the user presses a key for the first time, we should call runGame. This could be done with some if statements inside window key down, but I will do it inside window preview key down instead. I'll start by moving it up here next to window key down. And make it async. How does it work? When the user presses a key, then window preview key down is called, and after that, window key down is also called. But we can do something clever. If the overlay is visible, we set the event's handle property to true. This will prevent window key down from being called. So, while the overlay is visible, a key press will only cause window preview key down to be called. If the game is not already running, we set gameRunning to true. Await runGame. And when that method is complete, we set gameRunning back to false. Let's start the program and see what happens. The game opens with an empty grid and with the overlay visible. If I press a key, then the game starts. It's much better, but still a little abrupt, so we will add a simple countdown. It will be an async method with this signature. In the body, we loop from 3 down to 1. For each iteration, we make the overlay text display the value of I. Followed by a small delay. We can call this method from runGame. It should be done after the call to draw. Okay, it's time to see if it works. Are you ready? Awesome. The next thing we will do is provide a way to restart the game. To do that, we add a new async method called showGameOver. It starts with a 1 second delay. And then makes the overlay visible again. In show countdown, we changed the overlay text, so we must change it back to press any key to start. Back in the run game method, we know that when the game loop ends, then the game is over. So we will call showGameOver after that. And we also create a fresh game state for the next game. Let's see if it works. When the snake hits the wall, there is a 1 second delay, and then our overlay becomes visible again. Now I can press a button and play one more time. I think now is a good time to add some googly eyes to the snake. We will do that using the asset called head.png. In this image, the eyes are facing up, so when the snake is moving in a different direction, we must apply a rotation. To make this easy, we add a dictionary which maps directions to rotations. For the up direction, we don't need any rotation. For the right direction, we must rotate 90 degrees. For down, we need 180 degrees. And for left, we need 270 degrees. With that in place, we can write a method called drawSnakeHead. First, we get the position of the snake's head. And the grid image for that position. Next, we set its source to the head image. At this point, we must apply a rotation to the image so the eyes are facing in the correct direction. First, we get the number of degrees from the dictionary. And then we rotate the image by that amount. That's it. In the draw method, we will call draw snakehead after draw grid. Let me show you how it looks. Yeah, that's not quite it. The eyes are facing in the right direction though. What is wrong here? The problem is that the images are rotating around the upper left corner and not the center. We can fix that in Setup Grid. When we create the images, we just have to set render transform origin to the point 0.5, 0.5. This will make the images rotate around the center point. I will also reset the render transform of the images in Draw Grid. This ensures that the only rotated image is the one with the snake's head. Okay, check this out. Now it is easier to see where the snake is moving. But I want to make it a bit more clear when the snake dies. So let's add a method called drawDeadSnake. It starts by creating a list containing all the snake positions. The order in this list is from head to tail. Next, we add a loop. It has the same number of iterations as there are positions. Inside the loop, we grab the position at index I and decide the image source for that position. If I is 0, we need the image called deadHead. Otherwise, we need the dead body image. For the head, we don't have to worry about rotation. That's because the image will already be rotated correctly by the drawHead method. Next, we set the source for the image at the current position. Finally, we add a small delay. Now we just have to call it from show game over. Let's check it out. That looks pretty nice in my opinion. And it looks even better for a longer snake. What about other grid sizes? You can easily change the number of rows and columns as long as they are equal. But if I choose more columns than rows, for example, then this happens. That's because we have set the size of the game grid to 400 by 400, so the width to height ratio doesn't match the column to row ratio. This can be adjusted manually, of course, but we can also add a line of code in Setup Grid. I will leave the height at 400, but adjust the width so it matches the column to row ratio. Thank you for watching this video. If it was helpful, then consider leaving a like and subscribing to my channel. See you in the next video.